Hello everyone, my name is Nguyen, and this work is with Srinivas Akella at the University of North Carolina at Charlotte. Today I will present our work, Dynamic UGV-UAV Cooperative Path Planning in Uncertain Environments. I will first describe the motivation and problem statement. Then I will introduce the baseline strategies, our bidirectional strategies, other comparison strategies, and finally the experimental results. Here is a simple example of the problem we study. A ground vehicle starts at one location and needs to reach a destination. The road network is uncertain. Some roads may be safe, while others may be damaged, flooded, or blocked. The true damage to image at the bottom show real example of damaged roads and flooding after Hurricane Helene, which motivates this setting. This led to our main questions. Can we use a UAV or drone to inspect road segments ahead of the UGV to reduce uncertainty and help the UGV avoid unnecessary backtracking and rerouting? This problem is motivated by disaster response scenarios after floods, hurricanes, or earthquakes. In this situation, emergency vehicles such as ambulance or fire truck need to reach people quickly, despite many roads being damaged. However, a reliable map of road conditions may not be available immediately. If a ground vehicle discovers a blocked road too late, it may need to turn back and lose significant time. Our goal is to use fast UAV scouting to reduce this uncertainty. We model the road networks as a connected undirected graph G, where vertices represent location and edges represent road segments. Some edges are damaged or impassable, but these status are initially unknown. The UGV starts at SG and must reach the destination D. The UGV is restricted to moving along graph edges. The UAV can inspect edges to determine whether they are safe or damaged, and it can also fly directly to a vertex to begin inspection. The objective is to minimize the UGV travel time while avoiding impassable edges. In this paper, we focus on the planning component. So we have some assumptions, and the most important thing are once an edge is inspected, its status remains fixed. UAV has no energy constraints, and UAV can fly directly between vertices. The first baseline is the perfect knowledge strategy. Here, we assume that all damaged roads are known in advance. We remove these damaged edges from the graph and compute the shortest path to the destination. This is not realistic in practice, but it gives a lower bound on the best possible UGV travel time. The second baseline is the UGV-only greedy strategy. In this case, we do not use UAV scouting. The UGV repeatedly computes the shortest path using its current knowledge. If it encounters a damaged edge, that edge is removed from the graph and UGV return to the last vertex and then replans. This is the animation of the UGV-only strategy. The UGV start as a blue dot and need to reach the green dot. The brown part is mean that is the candidate sorted path for the UGV. And anytime UGV reach the damage point, they will need to reroute and find the new candidate path. For this strategy, the total time UGV need to reach the destination is about 130 seconds. Our main proposed strategy is the bidirectional strategy. The UGV first computes its current shortest path to the destination using current knowledge. Instead of assigning the UAV to inspect a critical edge, we assign the UAV to inspect the same UGV path in reverse order. Starting near the destination, the UGV move forward from the start, while the UAV inspect backward from the destination. Both continue until the next event happens. An inspection is complete, damage is found, or the UGV reached the destination. This strategy is simple, but it effective because it validates the tail of the UGV route early. And this is the animation of the bidirectional strategies. As you can see, anytime UGV has a candidate path, the UAV will try to inspect that path in reverse order. And in this strategy, with the same graph, the UAV only needs 100 seconds to reach the destination. In this paper, we also implement several UAV assignment strategies. Once the UGV receives a candidate path, each strategist uses a different edge critically measure to decide which edge the UAV should inspect. We evaluate the strategies on road network from the top 50 popular cities using the both small and the large maps. The table shows average UGV travel times for 5 large maps among the single UAV strategies. The bidirectional strategies often gives the best travel time. We also test multiple UAVs using the bidirectional strategies. Adding more UAVs can reduce the UGV travel time, but it also increase computation time because more candidate paths and assignments must be considered. The main takeaway is that UAV inspection can significantly reduce uncertainty in damaged road networks. This helps prevent expensive late rerouting and backchecking for emergency vehicles. The bidirectional strategy is especially attractive because it is simple, efficient, and performs well across most tested road networks. On the 15 lakhs mark, it reduced average travel time compared with UGV only by 26 to 38% for the 3 UGV to UAV speed ratio. Thank you so much for watching.